Darkness makes this look more impressive. It's a single 3 ohm resistance, and I measured 36 volts across it, so that's about 12 amps and 400 watts being dissipated. First, let's go into the gear ratios. So this is the first one where I've used a secondary ratio increase. It will work perfectly fine on direct drive, and I can still use it like that because the alignment is I can use the same length of chain. But this one, I wanted it to be able to put a lot of load onto the back wheel at very low RPM, so as to simulate like a really steep hill, for example. This is everything in highest ratio and generator shorted. Put my full body weight on the pedal. Even in the smallest chainring and the hub in underdrive, still get a decent amount of resistance. We're about 300 watts, about 80 RPM. And it also makes it feel more realistic as well, because this spinning mass of the generator gives it that momentum, a bit like a real bike out on the road, see, because it has weight. The amount of time taken to stop the generator by jamming on the rear brake helps to demonstrate the amount of energy stored. So the ratio here is 48 on the rear wheel of the bike, going to a 14 here. This is a 46 going on to a 17. So that gives a total of 1 to 9.3. So for every rotation of the rear wheel, the generator spins 9.3 times. One lesson I learnt from previous versions was just how much force is involved at high powers, pulling this towards the wheel, for example. So that's why I've got these metal stays this time to help support it on both sides, not these flimsy brackets like I used before. And also for this chain here, I've got this support, which is also acting as a chain tensioner. There's a bolt in there. And this here is alright because it's very well supported behind, and that's actually a bearing of a lawnmower deck. Moving on to the permanent magnet generator. This is one I actually built for a wind turbine and never used it. This is why there are bolts still hanging out of it. They are for the blades to bolt onto. Turned out rather heavy, these rotors. So I never actually managed to build a tower strong enough to hold it. It's using these ferrite magnets because neodymium suffer from corrosion. They are 40 by 25 by 10 mil thick, and I'm using them stacked on top of each other like that, which is why it's so thick, and so that's to get a little extra magnetism. There's the stator, which is cast. Here's an example of the stator. This is one I made as a practice run. It doesn't contain as much copper, about half as much, and there are a few mistakes. This side is a little bit thin, so we need coating if we're ever going to use it. The coils, there's 10 of them, and they're connected so that one end of the coil is connected to this ring around the edge here. So it's basically a star configuration. And the other end of the coil is connected to one of these wires. And the way it works is that you have a 12 magnet rotor. So when one magnet is directly over a coil like that, for example, if you go around quarter turn, so right there, it will be between the coils. And so what you end up with is a 5-phase generator, or it could be 10, I'm not really sure how you specify it, but I'll show you the wiring layout now. This has been drawn as if the stator has been straightened out, and I'm using inductor symbols as coils. As you can see, each coil is rectified, and you get the DC positive negative out here. So if we take a moment in time, for example, when a pair of magnets is opposite coils, it will be opposite coil 1 and 6, for example. Those two coils will both have either a north or a south pole opposite them, and they'll give either a negative or positive voltage peak out. I could reverse every other coil and so one would be a positive peak and the other a negative, and that would maximize the voltage out on the DC here. But in reality, because this is a 5-phase, if these were giving out positive peak, there'll be another phase which will be close to negative, so we still get a decent voltage out on the DC here. This is the rectifiers, the full bridge rectifiers. Each one of these wires is from a coil. It goes into a corner of the full bridge rectifier, and then you've got the DC. You've got positive, negative there. Ignore the wiring colours. So this is just what I had. Completely wrong. This is what I'm planning to use as a load if I'm not charging a battery, for example. Each of these heating element coils is around 3 ohms. So I'm planning to parallel them all up like this. We've got a whole load of them here, and that represents around about 1/4 of an ohm. And then use PWM to control the power dissipation. Don't do this, it didn't end well for the MOSFET. Trying to get a low pedaling resistance with a low load resistance using a very low percentage duty cycle on the PWM. If we do the maths I should have done in the first place, when the resistance is low, the generator will be spinning quite fast. So the open circuit voltage could be between 40 and 50 volts. So 45 divided by the resistance, 0.25, we get 180 amps, which is a bit above the rating pulsed current here of 160. So of course the MOSFET suffered and it failed short circuit. Change of plan. So I spent perhaps rather too long on a spreadsheet seeing if I could get the best range of resistances from the 24 sections of heating element that I've got, and this is what I came up with. So this represents these as in series. So we've got 5 series, 4 series, 3 series, 1 on its own, 3 in parallel, and 8 in parallel, and that gives you these different resistances here. And then I played around with switching them on or off, different combinations, and came up with these 20 different resistances. And then from that I picked out the ones that had a definite step between them, and what we get is these 12 here. So that gives me between 16 ohms and around 1/4. Made a start on the new version of dump load. This is all of the 24 elements, and I've started to combine some of them together with these bus bars. But I shall put the build of this in another video. So that's it for this one. Thank you for watching.